All right, so with any modelling question, typically we do have access to our CAS, and whilst it's not always the way, but I think the best way to sketch any of these functions, I get with any modelling, is first up, define the graph, okay? Now, we won't necessarily always define the domain at the end of the graph. We might restrict it later, and we'll talk about some pros and cons of that. So I've initially defined the function to be between 0 and 24. So you can see from my calculator there, I've got all the key points. Yeah. So once we've done that, I've just got to transpose that information onto my worksheet. So we know that it's a sine graph. The period is every 12 units. So I might just label the key values. I might decide that that's 12 and that's 24. A little bit cramped, which isn't ideal. The maximum gets up to 13. So there's one cycle, maximum, minimum, and we'll just try and use a ruler. Okay, and there's my average value in the middle. Sketched over the domain stating the period, the amplitude and range, show the coordinates of endpoints. So we can get that from our graph by analysing that graph. So that endpoint there is at 2410. The starting point, 0, 10. We can just come in here. My domain is from 0 to 24 inclusive. My range, well, it is 10 plus 3, 10 minus 3, so it's going to be from 7 to 13. Amplitude, range, so the coordinates of the endpoints. Okay, so they're the key things that I had to actually describe and state. Okay. Find the maximum and minimum temperatures. So with maximums and minimums with our trig functions, we just have to analyze, think about the graph itself. The sine function itself has a maximum positive value of 1 and a minimum negative value of -1. So if I put +1 in for sine, I end up with 10 plus 3. 10 plus 3 times 1, if you like, which is equal to 13 meters. And the minimum is going to be 10 plus 3 times -1, because the minimum sine value is -1, which is equal to 7 meters. So there's my maximum and minimum. The maximum occurs when sine is equal to 1, or when pi on 6, pi t on 6 is equal to pi on 2. So again, you can analyze your graph. You can do a range of things, but clearly from the graph, we can see at t equal to 3, and at t equal to 3, that's 3 a.m. 3 a.m. is the time. Our minimum time, we can again read from the graph, I should say. Sorry, the minimum occurs at 7 meters when t is equal to 9. And the first time that happens is at 9 a.m. Okay. Find the time of the day when the water first reaches 12.2 meters. So we're going to do that on our CAS. Solve the function equal to 12.2 for the first time, and we see that's at x equal to 1.5722. Now, what time of the day is that? So don't forget, the 1 is an hour, the 0.57 is the part of an hour. So if I multiply that 0.5722 by 60, I end up with 34.3 minutes. So that's approximately 1 hour and 34 minutes. So the time will be 1:34 a.m. In the same vein, we need t equal to 1:15 a.m., which is an hour and 15 minutes, which is 1.25, isn't it? Because 15 minutes of 60 is a quarter of an hour. So at t equal to 1.25, d is equal to, check it out on the CAS, 11.8 to 2 decimal places, 11.83 meters. Maximum is at 4, is it? That's at 3. All right, so we need to find a general solution of the equation when it's equal to 8.5. So let's solve. So we're looking to solve. I want to solve 10 plus 3 sine of pi x on 6 equal to 8.5. So 3 sine. What's that? Negative 1.5 divided by 3. So we got sine pi x on 6 equal to negative 1/2 if we bring the 3 across. So my general solution state, I have two forms for sine. We can write 2n pi plus sine inverse of negative 1/2 is equal to the angle, which is pi x on 6, or I get 2n plus 1 pi minus sine inverse of negative 1/2 equals pi on 6x. Yeah, so I'm going to be in the, I guess it's odd pi minus, even pi plus. So sine inverse, I've got my 2n pi, sine inverse of minus 1/2, or minus 1/2 is pi on 6, and it's minus pi on 6, or I'm going to expand it a little bit, 2n pi plus pi minus sine inverse of minus 1/2. We've already decided is that minus, or minus pi on 6. So let's just put a little line down there. So what do I get? I get, I'm going to take pi on 6 at the front. So I'm going to end up with 12n minus 1 equals pi on 6 x. So they cancel. So I get x is equal to 12n minus 1 as one general solution. The other, what have I got here? I've got pi plus pi on 6, which is 7 pi on 6. So if I took pi on 6 out the front, I'm going to get a 12n plus 7 pi on 6, which is plus 7, equals pi on 6x. Again, the pi on 6's will cancel. I get x equals 12n plus 7. So hopefully if I can compare that to the calculator dump, we can just see that if I just solve it on my CAS and don't put in a domain restriction or remove any domain restrictions I've got my 12n minus 1 is one solution, my 12n plus 7 is the other solution. Okay, so don't forget n is just any integer value. So if n is equal to 0, I get negative 1 and 7 as my first two solutions. So there's my 7 solution there. All right. Now, let's sort of interpret that now. So you can see what we're looking for. So graphically, that blue line there is the line of where y is equal to 8.5. So that's where the depth is 8.5 meters. And what I'm looking for is when the water is at least 8.5 meters deep. So the water is 8.5 meters deep. In that section there, all through those, in between those intercepts, my water is 8.5 meters deep. Yeah, so how does that correspond? Well, that's going to correspond to, well, it starts at least at, so between 0 and 7 hours plus 8.5 to, oops, not 8.5. And then we have to scoot forward to 11 hours, from 11 hours up to 19 hours. And then from 23 hours to 24. That's my 24-hour period. Now, I've got to convert them to times. So it's from midnight to 7 a.m., from 11 a.m. to 19 hours, 1900, that's 7 p.m., and then from 11 p.m. to midnight. So they're the times in the day that represent where that depth of water is greater than 8.5 meters. All right. Now, let's think about this one. Boats need a depth of W meters. Boats needing a depth of W meters are permitted to enter the harbour only if the depth of water at that entrance is at least a W meters for 1 hour, a continuous hour. All right. So what are we saying here? We need the water to be at least that deep for a total of an hour. So even if we just come down to my little graph here, there's my maximum there. All right. Now I need the water to be an hour for that depth or more, half an hour back, half an hour forward. So if I go forward 30 minutes and back 30 minutes, whatever that height is there, the water will be at least that deep for an hour. So we know that my maximum occurs at 7 hours. Where does this maximum depth? So I want 30 minutes prior, 30 minutes after. So I'm hoping, okay, so I've just got to fix up that CAS printout. So the maximum occurs, oh no, there we go, at 3 hours. So if I think of what the water depth is at 3.5 hours, or what the water depth is at 2.5 hours, both of them give me the same depth of 12.90 meters. All right. So everywhere from 2.5 hours to 3.5 hours, the water is at least 12.9 meters deep. So it's going to be at least that deep for 1 hour. So the largest value, so to 1 decimal places, is 12.9. So the largest depth of water we can have is not W, but the depth of water. W is equal to 12.9 meters deep. All right, so that's the deepest our channel can be for a minimum of an hour. All right, so if your boat needs more than 12.9 meters depth of water, it's not going to have that depth for more than an hour, or for an hour. It's going to be less than an hour. So you can't have any more depth. The depth can't be any greater than 12.9 meters. All right. Let's go down to our new function. Okay, so our new function, this is purely a calculator one, so we're going to think about this one. So a new function S of t is thought to model the height of water during the summer, where it changes. So what we're saying here is that S of t is equal to 0.9 times the previous function, f of 2t plus 1, between 0 and 24. Okay, so what I've done is I've defined that on my CAS. 0.9 times, my previous function was f1 of x, f1, and it's 2 times x plus 1 between 0 and 24 hours. So that's my new function, that's S of t. So when does that first reach? So I now need S of t equal to 11 meters, which on my CAS is f2 of x. And we can see it first reaches at 1.2, or after t is 1.2. So again, Oh, you can't quite see it on the printout. Let's have a look if I can move my printout a fraction. No, I can't. That 12.18 that I've got there, that's 0.2 times 60. So that's to get it into 12 minutes. So what we're saying then is that the time that we need is 1 hour. Oops. So after 1 hour and 12 minutes, it reaches 11 meters. So it's going to be at 1:12 a.m. Okay, so the 12 minutes is the 0.2 of an hour there. Find the first two coordinates of the points of intersection of the graph f of t and d of t correct to 2 decimal places. Now this is a really interesting one. Let's have a look. So what I've done, down the bottom right corner here, I've solved the two functions equal to each other, and I get at x equal to 0.9 and x equal to 10.6, the functions intersect. So to get the coordinates, I'm going to put 0.9 into the function, and I get the 0.9, 11.4, all right? Which we can see up in the graph above us, 0.9, 11.418, no problems. Have a look at my second point. My second point says at x equal to 10. Now, at x equal to 10, that's this point down here. We've missed completely that point there at 5.6. Okay, now to be perfectly honest, I'm not completely sure why the CAS produces that error or that omission, but I guess the little in the hazard symbol there where I solved f1 of x equal to f2 of x, you can see a little hazard sign. And if you click on that, it says there could be more solutions, which is great, isn't it? Which I guess is the little indicator that maybe you should investigate a little bit more. If we have a look at the alternative way of finding it, you'll note here I've got Mr. Rice to have a look at it. And instead of putting in the domain restrictions the way I have, if you go back up, you can see I've put in 0 to less than x is less than 24. Mr. Rice has defined both functions, then solve them equal to each other over the domain that we're required. And if you do it that way, you get that middle solution at 5.6. All right, that's the second one I needed. All right, so that's really interesting. So you can see the 5.6 and the 8.7 were, oh, well, that solution. The next one I found was the 10.1. So in actual fact, my solving of it skipped the middle two solutions and found the outside two. So I'll have to work on that and try and find out why. All right. So the first two coordinates of the points of intersection at x equal to 0.9 and at x equal to 5.6. I'll get at x equal to 0.9, we get 11.4, so that's one coordinate. And at x equal to 5.6, we get y equal to 10.6, that's the other coordinate. All right, so that's quite a little interesting little quirk, okay? But good question, difficult. As soon as we start transforming the function, that makes it more challenging. But anyway, have a bit of a look.